Hey guys, in this video we are going to graph a transform parent function, and that parent function is x cubed, which is an odd positive polynomial. And all polynomials, before we even get started, this should be fairly simple. All polynomials have a domain of negative infinity until, is this too light? Maybe, what do you guys think? A little bit too light, I think. How's that? I'm trying to make the colors look a little different, and I don't know. I feel like they're all looking the same. Maybe it's because my handwriting looks the same. The domain of all polynomials is negative infinity to infinity, and the range of all odd degree polynomials is also that same thing, all real numbers, negative infinity to infinity. So there you go. And we're not going to have any max or min for this graph. How do I know? Because I know what the graph looks like. So what does the graph look like, you ask? I'm glad you asked. Let's look. So this right here is the parent function for x cubed. If you watched the recent other video, we had the parent function of the cube root, which is basically this twisted and on its side. So you, from the point of inflection, over 1 up 1, over 1 up 7. Some of you asked if I could just plot 3 points if I'm graphing these, but I would suggest getting those 4th and 5th points, because if you only do these two, a lot of people accidentally draw the wrong graph, you know, because like it's very easy to kind of twist and pass through those points and go sideways or vice versa. So I would go for that 5th point, make sure it's clear that you're going up and down or side to side, like what does your graph look like, and really get that all done. But yeah, it follows this pattern. This is the distance between the perfect cubes. Okay, so we're going to take our transformations and apply it to that graph. Clearly list all transformations. So they are left 4 up 1. So we're going to start with that, left 4 up 1. And what am I going to draw there? Well, I'm going to draw the little crosshair. So left 4, 1, 2, 3, 4 up 1. So I have a little bit of that. That's where my graph is going to start. Then that will be my, oh, you barely could see that, huh? That will be my point of inflection right over there. Oh, because I'm being dumb and I'm using the highlighter and not the regular pen. Hello. So then I have another transformation. I have a vertical reflection, VR, and I have a vertical compression by a factor of 1/2. So instead of going up 1, up 7, and you're not going to fit it, but if you could, up 19, dot, 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 I'm going to do what instead? I'm going to do, well, down 0.5, down 3.5, and down half of 19 is 9.5. Okay, so this is me flipping and halving, taking half of all of my original up over here. So normally up 1, up 7, up 9 from where I left off, but I'm going to go down 1/2, down 3.5, down 9.5. And you're just going to go out 1 each time because that's what the normal shape is, and that part's not changing. So I'm going to go over 1, down 0.5, so right there. Over 1, down 3.5 gets me right there. Over 1, down 3, 6, 9.5, way down. I'm not going to see that. So that is something like that. And then to the side, over 1 up 1/2, over 1 up 3.5, over 1 up 9.5, somewhere up there, right? Because it's 4, way up there, further than that, but okay. So scoop it like that. Okay, there you go. Can't even see the top of it, can you? Okay. And that's it, right? Your concave up over here, so your concavity, it's decreasing still, but now you're concave down after that point of inflection. Then I might label, some of these values if you want it to be safe. If it's an assessment, I might label where the H and the K are, just so if you wrote down the wrong number, you could cover for yourself. So we got 1 is the Y value, and then this one should be -4. And there you go. I think that's it. All right. So check the playlist with almost probably 100 examples today. And the next video, number 6, will be up, and there's going to be 8 altogether. Bye.